Hello and welcome. This is the Taming Wild AI channel where we bring AI technologies out of the wild using the best practices of software engineering. In the last episode, we were able to execute 4 scripts from the author's implementation of efficient neural architecture search. CFAR10 macro search.sh performs macro search over convolutional networks of a specified depth. It searches through layer types and connectivity configurations for a network that performs well on the CFAR10 classification task. CFAR10 macrofinal.sh trains from scratch a network that was found from macro search. The script successfully trained a 24-layer network to 93% accuracy. But when we took an actual output from the previous script and gave it to this one, we ran into some errors, suggesting incomplete code. CFAR10 microsearch.sh performs microsearch over small, convolutional, and reduction cells. It also searches through layer types and connectivity configurations, but the cells it generates are repeated and then connected together to form a network that performs well on the CFAR10 classification task. CFAR10 microfinal.sh trains from scratch a network whose convolution and reduction cells were found from microsearch. The script successfully trained a network defined by the previous script to 93% accuracy. We identified several to-do items to tame this AI, including completing the functionality of CFAR10 macrofinal.sh. But we don't want to break anything that is currently working. Currently, to run any of these scripts to completion takes several hours on a GPU instance. We'd like to be able to test the functionality more flexibly and quickly. Then we can make modifications with confidence. Let's start with the first function, main, in main.py. This function depends on the global variable flags. Flags is populated from command line arguments by tf.compat.v1.app.run. In all paths through this function, messages get printed, the log file gets established, the flags get printed, and train gets called. This code specifies 3 possible paths. In the first path, the output directory specified in the command line arguments doesn't exist, so it gets created. In the second path, the specified output directory exists and the command line arguments say it should be reset, so it gets removed and then created. In the third path, the specified output directory exists, but the command line arguments don't say it should be reset, so it gets left alone. Let's write 3 tests to cover these 3 paths.
Let the code flow.
You might be wondering how we can test main without waiting hours for an entire training session to complete. These tests take advantage of unittest.mock, which was built into Python in version 3.3. You'll see that mocks allow us to test the logic in main without worrying about any other functions being called. This first test, mocks the print function so that we can capture what was printed without actually seeing it every time we run tests. It mocks isDear to return true as if the specified directory exists. It also mocks rmtree because we want to ensure it was not called in this path. It mocks makeDears so that we know it was called. It mocks the logger constructor to simply return standard out. And it mocks print user flags and train. Then it actually calls main. Afterwards, it checks to make sure certain messages were printed, that no directory was removed, that a directory was created, that the user flags were printed, and that the train function was called. The other two tests cover the other two paths. As you can see, these tests run very fast. If we want to sense for which code was actually executed during the test, we can use the coverage library. Now we can run the test under coverage. And get a report. This tells us that almost half of the lines in main were covered, and that the getOps function at lines 100 to 212 and the train function at lines 216 to 336 were not covered. I've written several more tests. The coverage on main.py is up to 98%. I must admit there is a fun factor in puzzling out how to hit different lines of code to get the coverage up. The reason some of these lines were missed is because one test is failing, and it is failing due to a defect in the code. If child sync replicas is set, then num aggregate must be also, but num aggregate was never specified as a command line flag. I've marked this test as known to fail, and I'm going to allow it to fail until this defect is resolved. One thing to keep in mind about testing is that unit tests like these are supposed to be independent. By default, the order the tests are run in is not guaranteed. This code depends on global variables and functions. If you set or mock them in one test, it could affect another test. Context managers are a great way to handle this, to ensure that values are stored at the beginning of a test and restored at the end. I've used the patch decorator from unittest.mock, which provides a context manager for mocks. I've also created a context manager for the flags global variable. This makes sure to restore flags to their prior values after a test ends. I've spent days writing tests to cover the code. It was pretty tedious, but it helped me understand the code better, and it gave me ideas for improvements to make. I ended up adding hundreds of lines of tests. The only changes I made to the original code were deleting some functions that were completely unused in the repository. The code coverage is close to 100%. That alone doesn't mean we've exercised every possible path through every function, but it's going to allow us to make changes with confidence. Confidence that we're improving the code without undoing work that was done before. Here's a typical example of a test. It tests the fixed layer method of the microchild class. The way I developed it was first to write a test that simply instantiates the object. When I ran that test, it gave me an error from the superclass init method. So I patched that method using the patch context manager. I ran the test again. I encountered another error from an imported function called by the fixed layer method, so I added a patch decorator. This required me to add an argument to my test method referring to the patched function. I added an assertion that the patched function was called. I ran the test again. I encountered an error from another method called by fixed layer. So I added a context manager returned by patch.object and an assertion that the patched method was called. Sometimes the function being tested performed an operation that I couldn't patch. In that case, I had to carefully craft the values returned by my patches so that the operation could be successfully performed. I continued doing this until the test passed. As you can imagine, I eventually ended up with exactly what I want, a test that checks a path through the code. The test runs quickly because calls outside the function under test are patched. If I modify the original code, the assertions at the end of the test make sure that the expected calls are still made, and the patch statements essentially document the external dependencies of the function under test. Also, these tests run fine on my 8 GB Mac Mini with no GPU. In the last episode, I made a list of changes I'd like to make to tame this AI. One of them was to rename the general child and general controller as macro child and macro controller for consistency with the paper, as well as the shell script that initiates the search. Now that we have a testing framework set up, the right way to make a change is to define tests for the change, observe them failing, and then modify the code to get them passing again. I'll start by renaming my test files. In these two files, I'll do a global replace of general with macro. When I run these tests, I'll get failures. And I can fix these with more global replaces. And that's that. Another change I wanted to make was to isolate the dependencies on TensorFlow. Every file in the repository was importing TensorFlow, and hundreds of lines called imported TensorFlow functions. I replaced those imports with imports of this new file. Here, I exposed the TensorFlow functions with the same names, but without unnecessary namespace qualifiers. This would probably be the first step in replacing TensorFlow with a different framework, but there are other benefits of doing this. The rest of the code is cleaner and lines shorter because of the unqualified names of the functions. For some functions, every call was using the same keyword arguments. I've exposed those as partial functions here. Partial takes the name of a function and some keyword arguments. It returns a wrapper function. The wrapper can accept arguments, but it adds the keyword arguments before calling the wrapped function. This reduces repetition of keyword arguments in function calls, making the rest of the code even cleaner and lines shorter. Many of the compat functions are raising deprecation warnings. By collecting them here, I might be able to update them in one fell swoop. Let's make another type of change that I expect will clarify the intent of many lines of the code. Data scientists often introduce temporary variables. For purely cosmetic purposes, they're trying to present a function as a sequence of subfunctions instead of as a composition of those subfunctions. Many years ago, I used to do the same myself. Then I read about a study that found that temporary variables were correlated with code defects. After that, I tried avoiding temporary variables and discovered that it's actually beneficial to do so. For example, here, W and X are introduced to hold the results of TensorFlow operations. W is used in the next line, and that result is never used again. It's not obvious that this is the case, but if we search for W, we see that the only time it is used again is when it is assigned to another result. So we can eliminate the introduction of W. X is also used in the next line, and then it is reassigned. So we can certainly eliminate this introduction. If we search for X, we see that it is reassigned to another result, so its previous result is never used again. So we can eliminate this temporary variable. Now it actually becomes clear that X and W were only introduced to add a composite operation to the layers array. By eliminating the temporary variables, we eliminate any question about whether they are actually used again. We also clarify the intent of the code. If this line is too long for comfort, we can break it up and indent it across multiple lines. We can also factor the computation out, but I don't think that is useful unless the same computation is used elsewhere. Let's run our tests again just to make sure we haven't accidentally broken anything unexpectedly. Yep, the only tests that fail are the ones we expect to fail on this machine and with the known defects in the code. I've gone through the code and eliminated many unnecessary introductions of temporary variables. Along the way, I frequently ran the tests. Good thing too, because occasionally I would make a mistake that was caught by one of my tests. This exercise did expose an unnecessary repetition of code. Here, whether separable is true or not, the exact same code is setting mask and then calling batch norm with mask on it. Only X is different. So we can pull this code out of the if statement and eliminate the duplication. This is a case where the introduction of intermediate variables caused the duplicate lines to be far away from each other, and therefore they were easier to miss. All my tests are passing except the ones that I expected to fail. I've made enough changes that even though my tests are passing, I'd like to make sure that the overall program behaves as expected. I'll run it for a few epochs on a GPU instance and compare the output with the output I saved before I made the changes. I ran all 4 forms of execution for a few epochs on a GPU instance, and they seem to be working as before. Macro search, macro final, microsearch, and microfinal. I moved the unit tests under the tests unit directory and the prerequisite tests under the tests prerequisite directory. I also created a tests integration directory. Here, I've added tests that take on the order of minutes to run, because they don't patch most of the external functions. These tests cover the layer printouts and variable counts for the 4 different forms of execution. In this episode, we wrote a large amount of test code. We started with the unit test library built into Python and used coverage to generate coverage reports for our tests. Using mocks and patches, we made sure that each test quickly covered a specific section of the code. Eventually, we got our code coverage above 95%. This exposed unnecessary imports and even an unnecessary file in the repository. The code coverage allowed us to start making changes to the code with confidence. We started by isolating the dependencies on TensorFlow in this new file, framework.py. Then we eliminated the unnecessary introduction of several temporary variables throughout the repository. These steps cleaned and shortened the code. With shorter code, some of the high-level control structures became clearer, and we were able to remove unnecessary duplication of code. We'll continue with deeper changes in the next episode. Thanks so much for tuning into this episode. If you found it instructive or useful, please share it with others who might as well. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments.